Okay. So, hi, I'm Michel, and I'm a fifth-year graduate student with Michael Carbin, and today I'll be presenting distributions for compositionally differentiating parametric discontinuities, and it's with these lovely co-authors here. So, automatic differentiation, or AD, is the automated computation of a derivative, and derivatives useful in deep learning, in optimization more generally, and in uncertainty quantification. And it's useful because it preserves program structure, producing an efficient derivative. So there are many libraries used in the wild, for example, PyTorch. And we give some example of the derivative of a sigmoid function here. So now let's see what these libraries do with a discontinuity, right? So we know that something isn't going to work out because discontinuities don't have a well-defined derivative at the point of the. So existing systems just go ahead, compute some derivative, and this is what they do. They ignore the condition, the parameter in the condition, and they take the derivative of each of the bodies. Body and the else body, right? So what if we want to differentiate an integral, right? So the integral is in the specification for the problem, and it computes the area under a curve, right? So this region from 0.5 to 1 is what we're computing. And the derivative of that intuitively should be negative. And the reason is if we move theta, we'll have a little bit less area, right? So let's see what happens when we use standard AD. So what it does is it effectively commutes the derivative in the integral. So it is now the integral of the derivative of our integrand. And the result is 0, right? So there's a question of what went wrong. Why did we get 0 here? And the reason is that the integral and the derivative don't commute. So we're not allowed to do that. But implicitly, these libraries commuted the derivative in the integral. So in this talk, we study a class of discontinuities that we call parametric discontinuities. And a parametric discontinuity is a conditional statement with a condition containing at least one variable of integration and at least one real valued parameter. So we'll start by showing the solution. And the solution is this interesting thing called the Dirac delta, which is this spike, precisely at the location of the jump discontinuity. And I'm just going to explain this Iverson bracket notation, which is 1 if theta is between 0 and 1, and 0 otherwise, right? So in this case, we have -1, because theta is 0.5. So why does this matter? Why think about parametric discontinuities? Well, these problems arise in physical simulation, in probabilistic inference, and in computer graphics. So for instance, when a ball bounces, the contact causes a discontinuity. And at the truncation points in a truncated Gaussian in variational inference. And then in computer graphics due to occlusion. And we'll look at computer graphics in a little more detail now. So in differentiable rendering, the goal might be to match a 3D scene to some photographs. And the idea is we start off with some initial guess, and we'll optimize to match that photo, right? And another example is image stylization. So we might want to have a triangulated stylized image, and we'll start with just uniform triangles. And we're going to optimize the locations of the edges of the triangles as well as their colors. And we get this cool stylized image. So Now we're going to dive into a simple example in more detail. And we're going to try to get a deeper understanding of these parametric discontinuities. All right, so is a program mapping the geometry and color of objects to an image, or a pixel grid. And here's the equation for computing the color of a single pixel. So let's walk through this. We have an integral, or a double integral, over that little orange region, right? And our integrand is basically the density of light in that enclosed region, right? So the first term says how light attenuates. So we're going to say for now that it has constant attenuation. And the second term basically says which way is the light pointing. It's pointing diagonally downward. And the rendered result is depicted here. So when we take the derivative with respect to the light's position, right, so we're shifting the area light, it should be non-zero because, well, the light was here, and when you poke it, it should be down there. So standard AD here is wrong because it misses that. And the correct derivative is just this diagonal, right, for that moving area light. All right, so this derivative really comes from two terms. The first term is the interior, which, because we had a constant shader, was 0, right? So this first term is 0. And then there's this boundary term as well. So in our work, we account for that boundary term, and an overview of the content in the paper. We provide an introduction to this lovely theory called distribution theory, and we provide some extensions. Implement Potto, which that's a Potto right there. They have spikes on their back, like a Dirac delta, but they're terrifying. Anyways, for distribution programming of parametric discontinuities, and we provide a denotational and operational semantics that we prove correct, and we show that our system supports separate compilation. So returning to this differentiable rendering example, there's this key feature of a renderer, which is something called separate compilation, which is that a program can be written as a composition of distinct executables. So in this case, we're going to try out 3 different shaders, right? So light can attenuate, well, not attenuate at all, attenuate linearly, or attenuate quadratically. And typically in the design process, you'll swap among these. And if you don't support that, that's a problem. So actually, our previous work wasn't able to support this, and now we support this. And in particular, programs can be separately compiled and differentiated, and then composed. And I guess the takeaway of this is you get this 2.73x speed up in compile time because you're not repeatedly compiling the whole program. All right, so going back to the contributions, now we know what separate compilation is. So let's revisit our previous example. And what we're going to do is simplify it a little bit more. And we're going to ask this question. Is there a of the Heaviside step function? So here's going to be our approach. We're going to take a sequence of smooth functions to approach that step function. And we're going to take the derivative of each of them. And we'll see sort of these derivatives slowly become more and more spiky until we get a function that's 0 everywhere, except at 0, where it's infinite. So this isn't a real valued function. And there's a question, how do you make sense of this, right? So it's something else, and it's called the distribution. And we're now going to give some intuition, right? So informally, a distribution is a generalization of a function that satisfies these nice properties. It's closed under limits, and under a generalized notion of derivative. So the first way to reason about this Dirac delta is to basically typecast your derivative to a distribution, or to lift it to a distribution, and then take the limit. And then because of the closure under limits, you can show that Dirac delta is a distribution. Alternatively, you can lift to a distribution, apply this generalized notion of derivative, and then because there's closure under this generalized derivative, you can show that delta is a distribution. So sort of the inspiration for this two diagram came from a property of smooth functions. And the idea is that if you have a sequence of smooth functions that approaches another smooth function, then the sequence of derivatives approaches the derivative of that function. And so here, we did sort of the same thing, except we approached a function that wasn't smooth. And then we got something that's supposed to represent its derivative. All right, so we're going to follow this formal plan, which was one of the two ways we showed earlier to formalize, and closely matches our language formalism. So in particular, we're going to take this heavy side. We're going to lift it to a distribution. Right? That's our typecast. And then we're going to take the distributional derivative. So what class of functions can be lifted to a distribution? Well, it's locally integrable functions. And those are functions that are integrable on every compact set in its domain. So the one function is not integrable because the integral from negative to infinity is infinity, right? So not integrable, but it is locally integrable. And the singular function is not locally integrable. So this T operator takes in a locally integrable function, and it works by integrating that locally integrable function against a test function, which we'll talk about later. And we discussed how to lift a function to a distribution. And so what is a distribution? And why is T sub h a distribution? Well, I'm not going to go into too much detail here, but it's a continuous linear functional. And the main thing, well, quickly, a test function is a smooth function with compact support, right? So its distributions are over the space of test functions. Test functions are smooth functions with compact support. And it's a functional, which means that it takes in a function, in particular, a smooth function with compact support, and it returns a real number. And that's why I was lifting. We're really changing the type, right, from a function to an integrator. It's linear, and it's continuous, which basically means the limit is preserved through distributional application. All right, so now we'll define a distributional derivative. So this generalizes the traditional derivative, and it ends up being the negative distribution applied to the derivative of the test function. And we have some derivation here from first principles. You don't need to follow it. Where the main takeaway is that we can derive, using just these rules, that the distributional derivative of the heaviside function lifted to a distribution just point evaluates the test function at 0. OK? So we've defined distributional derivative. And now you might be saying, what's the relationship between this delta thing you wrote and the distributional derivative of this heaviside distribution? Well, it's really just convenient notation. So this is like a generalized notion of integral that is paired with this Dirac delta and that acts by point evaluating the function you integrated against. Right? OK? So these two notions point to the same functional. And this informal picture and this formal picture coincide. All right, so how does this all relate to programming? Well, we have some little language with some arithmetic terms, as well as an conditional and an integral. And we're going to look at the same example as before. And we're going to give it some pretty standard denotational semantics. And the main interesting thing is typically we give denotation to an if statement via cases. But here we're going to write it as a sum of heavy sides, right? So this is if body times heavy side plus else body times 1 minus that heavy side. And this is suggestive of a distributional derivative of a heavy side that we might take, right? And so we can also define this distributional derivative denotation that maps programs into distributions. And the main property that it satisfies is that the distributional denotation is equal to the denotation lifted to a distribution, and then the distributional derivative of that, right? OK? So we can apply the same distributional denotation to our example. And the takeaway is we get a Dirac delta, right? So in conclusion, our formal picture and our semantics match up, right? And we can do the same sort of thing with the integral and apply it to our example for the regular denotation. And the distributional denotation we'll leave to our paper. So the key idea here is that we introduce a notion of distributional derivative that does commute with the integral. That wasn't true before. And now it's true. And that's the notion that this is compositionally differentiating, right? And we prove correctness. So the results that you might expect of these two semantics, we prove them. They're in the paper. And we also provide a full operational semantics, which we show is an unbiased and consistent estimator of the denotational semantics. And I guess the key idea of our implementation is we sample those Dirac deltas. So for example, this step function, which jumps at theta, and then when we take its derivative, we have a Dirac delta at theta, will sample the point x equals theta, which otherwise wouldn't be sampled. OK, so these are, again, the contributions. And now we can look at some applications. So one is risk minimization. And here we optimize this truncated distribution, which is dashed, to match a Gaussian. And we can see if we use standard AD, it can't move those boundaries. But if we use our system, it can move those boundaries. And we implement a 3D differentiable ray tracer. Not going to talk too much about this, but we can see the original programs and their derivatives. And then we do some benchmarking. And the main takeaway is compared to our previous work, TEG, the compile time is much faster on this benchmark. And the evaluation time is faster as well. And the reason is separate compilation, right? So separate compilation meant that we're not doing these global program transformations. So our ASTs are nice and small, and that's good. And finally, there's some related work to this is previous work that I did with co-authors. And the idea is to directly sample these boundaries. And then there's another line of work that blurs out the discontinuities. And the issue is you need to tune some parameter. And it's really hard to prove correct because you're changing your spec before you differentiate, right? So in conclusion, parametric discontinuities are everywhere. They're in physics, probabilistic programming, computer graphics. And we provide the first language formalization that accounts for parametric discontinuities. And our future work is lots of more language features. Our language is quite simple, actually. which we list out language features. And these techniques, I think, will be broadly useful in implementing differentiable PPLs, since the derivative of a measure is a distribution. So the distributional derivative of a measure is a distribution, but the derivative of a measure doesn't necessarily make sense out of the box. So that's interesting. And more broadly, I think it would be interesting to build world models using a mixture of neural networks and differentiable rendering and physics. Thank you.
OK, maybe one quick question from the audience.
Totally. Right. So maybe it's worthwhile I went a little quickly. There are limitations, and one important limitation is that the condition in your conditional should be piecewise invertible, or at least locally invertible, and you have to know that inverse. So as of now, if you want to give that analytically, that's some significant programmer burden. And there's actually work by Elias here on automating that. There are ways to do it, but that's definitely a challenge. Another challenge is the Dirac delta sort of has to know how large the jump is from one side of the conditional to the other. So you end up needing to evaluate both sides of the conditional, which might be a little unintuitive to users. So those are maybe two challenges. And then also just implementing sampling the way we did. It's a little tricky to implement, but I don't think that'll be the barrier. Yeah. Thank you for the question.
OK, so thank Jesse again for his wonderful talk. And